So now let us go into a little problematic system. So this is NO2. Nitrogen. This class of compounds are called NOx because it has nitrogen and oxygen, and they are my favorite compounds. They have importance in atmospheric chemistry, energy research, health research, many of it. So now we will do the optimization of NO2. So it has one unpaired electron. Oxygen, the two oxygen has 8 electrons. This is N has 7 electrons. So one unpaired electron. So it's a doublet. Let us try first with the Avogadro. Let's make the structure. I don't need the hydrogen here, and now I need to add the two oxygens. Okay, I can do a pre-optimization, and now I can make my OCA input file. This will be of course 2. We are using, we cannot use RHF here. So either we have to write UHF, or even if we do not write anything, it will automatically take UHF. And this will be opt because I want to optimize. The basis set is written here as def to 1T is extra. So it will be def to TZVP. We can happily use Rij cos x, and we are ready to go. Okay, we should have written HF, otherwise it will not know which method you are going to use. Okay, so let me generate the open shell. So it is here. So today to run the calculation, we will use something called MOBA-XTerm. So MOBA-XTerm is, let me first open it and then I can show you how it looks like. So I will start my local terminal. Okay. So this MOBA-XTerm actually gives you a Linux-like environment in Windows. So this helps us to use many of the commands which are available. So we have perfectly all the Linux commands you have, it will work here, and you can also use it to connect to remote machines. So if you want to submit your job on some remote desktop, maybe some workstation or cluster, this is a very helpful tool. You can connect it through this. You can download this one from this link. So there is a free version, so you can download and use it. Of course, whatever calculations we are going to show, it can be done with PowerShell also. I think there is absolutely no problem. The reason why I will use it here, because this will help us to see when the job is progressing, how the calculation is progressing, because I can tell and see the output file to see how the jobs are progressing. So that is why we are switched to MOBA-XTerm. You can do every calculation the way you are doing up to now in the PowerShell. So the everything is same. The command is orca, and let me see what is the input file name I have given. I have given it NO3. I think a good idea to go to the properties and rename it at NO3HF, because this is Hatrifog. And so it is orca. Oh, this is not NO3, it is NO2. No, mistake. NO2HF.INP. The only additional thing I will do here is I will put an ampersand. So what the ampersand will do, it will bring back the prompt and put the job in the background. it says that cannot open input file. I can list it. Oh, we are in a wrong folder. Some mistake we did. We should have started from here. Like the way open in terminal, we can write open Mobax terminal here. Now it's here. So the command is same, no2 hf.inp. I will give the ampersand, so it will put the job in the background. Then how this calculation is progressing, I can use by this command tail. Tail means you are just holding the tail of the output file, the end of the output file. So if you write tail minus f, you can actually see how the file, how the calculation is going on. You see the SCF is going on. So if your initial geometry is bad, initial SCF can have some convergence issues, and you see that this is not converging very smoothly. So it's iterating with, like, it's actually fluctuating between the iterations. So then it changes the solver automatically. It says maximum gradient error decreased only by a factor of 1.1. So it's goes to what is called a tri SCF, which is a second order SCF, and it's actually much better convergence behavior. Of course, it's an order of magnitude slow. And with the second order SCF, at least you can see that it's going towards convergence, not very smoothly. So now you can see it's the bond length and bond angles are changing. So my initial geometry was not great, and which was 128. Now once the geometry become little better, you see that my convergence has become much faster. So within 14 iteration I have got convergence. So currently the bond length is 1.22, the experiment is 1.193, so at least it's going towards some direction. Again, the convergence are faster. So it says that although the strict convergence criteria are not matched, but it has converged enough. So reasonable convergence of the gradient will be increased, and so this has put as a convergence is achieved. Now you can see one interesting thing is that the two bond length of NO2 is different. Maybe I can open it now, this one in using Chemcraft, and I can show you how the output file looks like. So it's 1.25939, 1.25923. So there is a slight difference in the fourth digit. So this actually happens due to the fact that our optimization criteria are not very tight. So if you calculate frequency, you may see slightly imaginary frequencies. So our option is to use the so-called tight opt, but this may not be necessary in this present case. So let us do one thing. Let us again open an Excel sheet. The same opt Excel sheet we were using, and I have made here a second sheet where I have given the parameters for NO2. These are the experimental value. Now let's see. how much was the results. So, okay, once this calculation is converged, then you do another SCF to give you the final energy point. Just see here something interesting. The expectation value of the square operator is 1.1254, whereas the ideal value of the square operator for a doublet should have been 0.75. So, it is heavily spin contaminated, and the spin contamination can sometimes lead you to trouble. So, I can take one of them, not a problem, 1.2594. And the angle is 110.06. So, you can see that my bond length and bond angle are quite off. So, this country fog here is not a very good method because it is heavily spin contaminated. Let us see how the GFT calculation took. So, it took around 3 minutes 53 seconds. You may say that it's not quite high, but let us see how the DFT actually does. So, the way I will do it is that I will open the NO2HF input file, I rename as NO2 B3 lip .inp, all files save, and in place of HF I have written B3 lip. Now, let us try this one. Orca, same thing, NO2 B3 lip dot input, NO2 B3 here the sum of the individual time. Let me copy it, and maybe here we should put a column time experiment. I have no clue how much time takes to do this kind of experiment, but this one I can write time, and this bracket I can write in seconds. One interesting thing to see here is that the spin contamination is actually smaller, although it says that it is a DFT calculation. We have discussed this one, that DFT wave function actually does not have any physical significance. That is a fictitious wave function to put there to fit the kinetic energy part. But if you calculate the spin function by taking the same determinant, you can see actually the amount of spin contamination is quite small. Should be pretty close to convergence now, maybe 1 or 2 iterations. So, here also it is almost there. So, it has the convergence has declared it has convergence. So, now here my bond length is 1.9, 1.19 something was there. Let us see it. So, it is 1.1909, 1.1909 if I am reporting up to 3 digit. Okay, that's also one should mention. This 259 I should write as, because the experiment is given up to 3 significant digits, so I should also put my values also only up to 3 significant digit. This is 1.191, I shouldn't write, and the angle is 134.4. Let's check the time. It's 230.906. So almost at the same time, you get a much better agreement relative to Hartree Fock when you use a DFT functional B3LIP. This agreement may not be so good for other functional, but almost for every case you actually get a better agreement than the Hartree Fock if you are using DFT. Now, if I do the calculation of the MP2, of course, it will take much more time. I am not going to do the calculation, I already have done the calculation, so I will just use the output file. So, you can see it is already taken 4 minutes for the calculation, but more than the timing, let us see the values. Of course, it is a small example, so it has taken long time, small time, because remember the formal scaling is of MP2 is n to the power 5, and the n to the power 5 scaling depends upon the number of electrons. So, of course, when your number of electrons are more, your difference between the DFT timing and the MP2 timing will be much more. You can take one of them. I will take 1.199. And the angle is 134.11. So, MP2 can give you similar result, but at a much higher computation cost. So, B3LIP is good for almost all practical purpose. Actually, B3LIP is sometimes becomes costly because it's an although it has a formal scaling of n to the power 4, Rij cos x can speed it up. The better approach is to go to the so called GGA or a meta GGA function which does not have any exchange. So, you can directly factorize using Hartree Fock. So, now let us go to this example of aniline, which we want to optimize using RIBP826. So, this is a slightly larger example, and here we show you what are generally the good strategies when you are optimizing a large molecule. Let us go to Avogadro. And to generate the alanine structures, let us first build it. So, we go to the insert option, and this alanine is a peptide. I select the alanine, insert the peptide. So, this alanine is here. I go to ORCA, I make it opt. RIBP 86. In principle, you can use the D3. I have not using the D3 here because I just want to show how one can optimize quickly, efficiently, rather than to get into the accuracy of the optimization. So, this is what I will do. I will generate the input file as, let us say, alanine. I will not run it here because it will take some time to run it, which may not be, may become boring while we see it in the screen. So, I have already run it and I have the output file. So let me open this one in ChemCraft. Okay. The other thing which I have not done, I should have been done. After I do the optimization, how do I know it's a minima or real minima or transition state? The way to understand is to calculate frequency. So this I should have been used with the frequency by looking at the output file. Actually, I remember that I should have calculated the frequency also, and the frequency would have told that these are this is actually a real minima or not. So once you run this calculation, you will get an output, and if I open this output in the ChemCraft, you will get the frequency. You can see all the frequencies are actually non-imaginary. So this means we have optimized to at least a local minima, and if you go to the optimization step, this is how the optimization steps will look like. If you want to see how it has been optimized, you can see the rotation and try to see how this is going to actually the minimum energy structure. And of course, there is a tool. If you go to this tool, okay, from here you should click the optimization step, then you can go to the tool, so optimization convergence. I want to see energy versus step n. So see, this is how this has taken 15 step, and this is how it has went to the minimum. And you see that the initial decrease was there, then there was some flip flop, and after step 8 they are generally have went into very smooth convergence. So it's 15 step taken, and if I open the output file and I go to the end, no, I have not opened it here. Let me open it with the notepad. This has taken around 4 minutes. I wanted to avoid the unnecessary timing. So how you can accelerate the convergence? One important option is to accelerate the convergence is that you can supply the Hessian. Remember, in any optimization algorithm, when it tries to find out the minima, it not only, so it will start from the hill and it will start to come down. When it come down, there are two things important. First of all is the step size, and the step size should be such that it does not overshoot the minima. The other important thing is that the sign of the steps, so which direction the step should be taken, and which direction the step should be taken is generally decided from the Hessian matrix. And this Hessian matrix needs, for any optimization step, what most of the optimization program does is that it calculates a very quick Hessian using the some force field and then update it as it goes along the optimization. Now, sometimes these updates are not very successful, especially if your initial structure is very bad or if you are dealing with a very floppy molecule. The updated Hessian is not good. So, it is generally a good idea to recalculate the Hessian at every step. And the way you can do this in Orca is by adding this block to your calculation. This is called geom calc Hess true. That means it will calculate. So, during the geometry optimization, it will calculate an exact Hessian, and after 5 steps it will recalculate the Hessian. And if analytic Hessian is there, you can calculate it analytically, otherwise you can use a numerical Hessian by putting these additional keywords in the same block, which is called numerical, that num Hess is equal to true. So, let us do this. Save as llin.hess. And because I am skipping, so I put these keywords here. Now I save it again. Of course, I am not going to run the calculation. I have already run it, so I will just show the output file, because running it in the class will take a lot of time, because I am skipping, you should not skip it. You should take the time and run it and actually look at the output file. So, this is the Hessian.output file, it is already there. I open it with the ChemCraft. Here also you see there is no imaginary frequency, so it is fine. So, here you see it was converged in 15 iteration. So, if you recalculate the Hessian, you calculate the Hessian in the beginning and recalculate at every 5 step, go to the tool, show the optimization convergence, it actually takes more step, and you see that there are in between there are jumps, and these jumps you can see that these actually correspond to where the Hessians is recalculated. At 5 it is around 15, around 10 also there is a jump. So, if you want to see the animation, so just recalculating the Hessian, although many people suggest that recalculating the Hessian is a good option, it may not be a good option in every case. I am not saying that the recalculation of the Hessian is a bad thing. Recalculation of the Hessian is important if you are dealing with a very floppy structure or very bad initial structure, but in many cases it does not reduce. So, if it is not converging at all, recalculating the Hessian may converge it, but recalculating the Hessian will not reduce the convergence step in most of the cases. So, if you want to see the animation, you see that whenever there is this, like remember there is a 15, there is a jump. So, what happens is that whenever there is a Hessian is calculated, the other bonds get readjusted quite well. So, then what is a good option to optimize it? To me, the good option to optimize it is to use the two-prone strategy, and that two-prone strategy is first optimize the structure with a low level method. Low level method can be anything, it can be like it can be a cheaper method, like say if you want to optimize in final optimization in MP2, you may want to do the initial optimization in a very small basis set using let us say DFT GGA functional. You can use XTB. XTB is an extremely good option which gives you a very good initial geometry. Here I have given an input file with XTB. I don't know why I have given this dep2 SBP. It does not anyway matter because this is not going to use that dep2 SBP. So, what I am going to do here, I will just copy paste, open a new file, and I will save it as maybe alanine only. So, now see I am recalculating the Hessian and at each 5 step, and the initially also you also calculate the Hessian, and of course, I am calculating the frequency. So, at the end there will be also a Hessian calculation. Now, if I calculate this one, okay, I have to go back to the previous cell. I can go back to using a Linux terminal only, but let me show you how you can do it here. You can reopen here using MOBA XTerm terminal. I have written a wrong spelling here. XTB optimizations are super fast even with frequency calculation. So it's only 32 seconds. If you want to see how many iterations it has taken, after 22 cycles it has taken. Although it has taken 22 cycles, it's actually happened in 30 seconds only. So it's good. Now once I have optimized it in my initial structure, then what I should do is that I can redo the calculation. This should have been BP86, RI BP86. So I did the initial calculation with XTB, and then I can make another Hessian. Let us say I make a new file and let me copy it, and then I can change the things. So RI BP86. So now what I will do, I will read the Hessian which from an initial file, and if I go back here and if I see my file name, the file name is called alaline.hesh. So here in place of, so the name of the Hessian file should be same as what is generated in the previous XTB step. So it should be alaline.hesh. If you give a different name, then it will not be able to read it. My XYZ file is alaline.xyz file, so which is optimized from the by using XTB. I given RIBP86 of frequency, and I can save it as BP86 only. Maybe I should have given a better name, but for the time being BP86 should be fine. So I have saved it. Now let me go to Orca, BP86.inp. So there is an error, and the error goes to my XYZ file, which I have made is as alaline.xyz. So you have to be careful about the name you are giving. Now it should run. I have rerun the running calculation, not a problem. I think if we wait a little bit, 30 seconds it was. Okay, it's done. Now we go to BP86 one. So BP86 in many of the cases it was taking 15, 24 step. Alanin is a slightly larger molecule, so sometime it can take some time. So 2 step, this is the 3rd step going on. So it's already there, almost close to the convergence, maybe one more cycle. So you see it's converged. It has converged only in 4 cycles. So which was 15 cycles before without the any Hessian calculation, or if the actual number of Hessian calculation actually increase the number of cycles required. Now if you do this 2-step optimization process where you first initially pre-optimize using a lower level of method, maybe XTB, and then optimize with the actual method you want, this actually reduces down to much lesser number of cycles. The philosophy is that when your structure is far away from the equilibrium, your optimizer requires a lot of cycles to find out this one. So this low level of optimizer, although this cannot find the exact minima, it will bring you close to the local minima, and once you close to the local minima, your optimizer at higher level of method can find out the local minima in only very few cycles. So this is what we wanted to discuss about optimization. You have a homework problem, and this you should definitely try. How you should try its, which kind of optimization you should try, which kind of optimization do you think is the most appropriate one, you let me know. So the compound is cobalt acetyl acetone 3, and you need to optimize it in RIBP 86 step 2 SVP. How you make the structure, it's up to you. I can give you hint that you can actually use the Chimera X. I would have made it with the Chimera X, but that's up to you how you want to make the structure. So you let me know how the optimization goes through.